Alright, in this video we study Napier's constant, that is E equals to 2.718 and so on, as the limit of a certain sequence. Okay, let's start. So this constant called Napier's constant can be obtained as the limit of this sequence 1 plus 1 over n to the power of n. So if we define this sequence an as 1 plus 1 over n to the power of n, then we want to show that the limit of this sequence converges to this value. Actually, what we prove here is that the converging value of this, the limit of this sequence is somewhere between 2 and 3, which is indeed true. Before that, let's see some of the values of this sequence. So A1 is obviously 2, and if you calculate A2, that will be 2.25. And if you continue this, let's say A3 is 2.370 and so on, and A10 would be 2.593, and A100 would be 2.704, and A1000 is 2.716. So it's getting closer and closer to the limit value of 2.718 and so on. And as you can observe, this seems like a monotone increasing sequence. See, this is less than this, which is less than this, and so on. So it's as n goes bigger and bigger, the value of the sequence seems to increase. In fact, that is what we are going to prove now. So this sequence, defined as 1 plus 1 over n to the power of n, is monotone increasing. So now we try to prove this theorem. Okay, so let's prove this. And an is 1 plus 1 over n to the power of n. Now we expand this by using the binomial theorem. Okay, so by using this, that will be n choose k and 1 over n to the power of k and 1 to the power of n minus k. In case you forgot the binomial theorem, is this: a plus b to the power of n is this, n choose k, a to the power of k, b to the power of n minus k. Okay, in this case, b is 1 over n, and a is 1 over n, and b is 1. Okay, so this is just 1. So, and let's expand, write down n choose k explicitly. That's number of combinations. N factorial, k factorial, n minus k factorial, and 1 over n to the power of k. So this one is just 1, so I'll skip it. Now, let's combine these terms together to define sk. So that is n factorial over n minus k factorial times 1 over n to the power of k. Now, if you cancel common terms in here and here, we have n times n minus 1 times up to n minus k plus 1 n over n to the power of k. Okay, so here in the numerator we have k terms, k factors. Okay, from n to n minus 1 to n minus k plus 1. So there are k terms. And here we have n to the power of k. So that can be written as n times n times n times n, so on times n. So again, k terms here, k factors here. So we can write this as n over n, so this n and this n together, and this n minus 1 and this n together, n minus 1 over n minus 2 over n, and so on, n minus k plus 1 over n. Okay, so the first one is 1, and this one becomes 1 minus 1 over n, and this one becomes 1 minus 2 over n, and so on, and so on, and we have 1 minus k minus 1 plus over n. So by using this sk, an can be written as, let's see, an can be written as the sum over k from 0 to n and sk over k factorial. Next, consider the next term, that is an plus 1. So according to the definition, this is 1 plus 1 over n plus 1 to the power of n plus 1. Again, let's use the binomial theorem. We have k from 0 to n plus 1 in this case. And n plus 1 choose k, and n plus 1 to the power of k, and 1 to the power of n minus k. So again, okay, let's write this factor explicitly, k from 0 to n plus 1, and n plus 1 factorial, k factorial, and n plus 1 minus k factorial, and 1 over n plus 1 to the power of k. Okay, now let's combine these factors together to define tk. So n plus 1 minus k factorial and 1 n plus 1 to the power of k. So if you cancel the common factor in here and here, that will be n plus 1 times n times n minus 1 and n. So up to where? There should be k factors, right? So it should be k n minus k plus 2 over n plus 1, n plus 1, and so on, n plus 1. So here in the numerator and the denominator, we have k factors each. So let's combine them together, just as we did for sk. That will be n plus 1 over n plus 1. N over n plus 1, n minus 1 over n plus 1, and so on, n minus k plus 2 over n plus 1. So if we simplify, okay, so this will be n plus 1 minus 1. So it would be 1 minus 1 over n plus 1. And 1 minus 2 n plus 1. And 1 minus, what is it? K minus 1 over n plus 1. Okay, so now using this tk, the term an plus 1 can be written as this, n plus 1, and tk over k factorial. And so this summation contains n plus 2 terms. Okay, so k varies from 0 to n plus 1. So let's pick first n plus 1 terms. So 0, k from 0 to n, tk, k factorial plus the last term will be k tn plus 1 over, so k is equal to n plus 1, so n plus 1 factorial. Okay, so let's compare this summation with this summation. Okay, both contain n plus 1 terms. And each term contains k factorial in the denominator here and here. So if we can show that for each k, sk is less than or equal to tk, then we are done. Okay, so let's show this. Show this. Okay, so sk is this. Let's copy and paste here. So sk is this thing. Okay, paste. So this is sk. And tk is this. Now compare each factor here. So in both of these terms, we have k factors, okay? K factors. 1 over n, 2 over n, and up to k minus 1 over n. And we have 1 over n plus 1, 2 over n plus 1, k minus 1 over to n plus 1. Okay, they are very similar except for these things. So this is either n or n plus 1. Okay, now we have n is less than 1 over n is less than 1 over n is greater than 1 over n plus 1. So if we put a negative sign, then the inequality is reversed. And if we add 1 to the both sides, we have this. Okay, so for this term and this term, we have this inequality. And for this term and this term, we also have 1 minus 2 over n less than 1 minus 2 over n plus 1, this inequality. Okay, so each of these factors we can compare, and always it is this term, this factor, that is less than this factor. So if we multiply all of them, and of course all of them are positive, okay, because 1 over 1 n is always less than 1, and k minus 1 is less than n always. So all of these terms are positive. And so if we just multiply all of them, each of these terms are smaller than each of these terms. So we have sk less than tk. Okay. Of course, if we divide both sides by k factorial, we still retain the same inequality. And if we sum over all k from 0 to n, the inequality is still retained. And if we add to the right-hand side of this, tk k factorial tn plus 1 over n plus 1 factorial, of course that is greater than the leftmost side, hand side. Okay, therefore an is less than an plus 1. And we have proved that this sequence is indeed monotone increasing. Now we have already seen that a1 is this, which is 2. So that means, and also we have just seen that this sequence is monotone increasing. So that means for all terms we have this inequality. So for any n, an is greater than or equal to 2. And next, we show that this is less than 3. Okay, to prove this part, we use the previous expression we have used to prove the monotone increasing k from 0 to n and sk over k factorial. So when k is equal to 0, this term is 1. When k is equal to 1, it's also 1. And for s k equal to 2, let's just leave it like this. K 2 factorial. And s3, 3 factorial, and so on, and sn and n factorial. Now, recall that each sk is 1 times 1 minus 1 over n times 1 minus 2 over n times and so on, up to 1 minus k minus 1 over n. Okay, and each of these factors is less than 1, and it's positive. So if we multiply all of these factors, then that is less than or equal to 1. So if we use this inequality, so each of these sk's is less than 1. So that means an is less than or equal to 1 plus 1 plus 1 over 2 factorial. So replace this with 1. And 1 over 3 factorial, and so on, and 1 over n factorial. Now, next, look at these factorials. Okay, so k factorial is 1 times 2 times 3 times and so on up to k, right? And this is less than 1 times 2 times 2 times 2 times and so on. So just multiply 2. So these are k minus 2 factors and k minus 2 factors. And we have k minus 2 2's plus 1. So this will be 2 to the power of k minus 1. Okay, so k factorial is greater than 2 to the power of k minus 1. So by using this, we have 1 over k factorial is less than 1 over 2 to the power of k minus 1. Okay, now we use this for each of these terms. Then we have an is less than or equal to 1 plus 1, so this 1 plus 1, and plus 1 over, so this is 2, so 2, and 1 over 2 to the power of 2, to the power of 3, and so on, up to 1 over 2 to the power of n minus 1. Okay, so if we consider these terms, then this is the sum of geometric progression. And if you remember the formula for the sum of geometric progression, that's fine, but I don't remember, so let's derive it right now. So let's say S is the sum of this geometric progression, and up to 2 to the power of n minus 1 here. Okay, so let's multiply both sides by 1/2. Then we have 1/2 plus 1/2 squared, 1 over 2 squared, 1 over 2 to the power of 3, and so on, and 1 over 2 to the power of n. Okay, so, and take the subtraction, difference between these two. So the left-hand side is 1 over 2s, and the right-hand side is, so this cancels this cancels this cancels this, and so on, and everything is cancelled except for this one and this one. So the right-hand side is 1 minus 1 over 2 to the power of n. Now S is, so multiply both sides by 2, and we have this. Okay, now substitute this into here. So an is less than or equal to 1 plus this summation. So 2, so let's say 2 minus 1 over 2 to the power of n minus 1. Okay, so this is 3 minus positive number, which is less than 3, of course. Therefore, for all n, we have that each term is greater than or equal to 2 and less than 3. And we are done. So we have seen that this sequence, 1 plus 1 over n to the power of n, has the following properties. 1, it's monotone increasing. And 2, it's bounded. So bounded below and above. So these two facts indicate that according to the monotone convergence theorem, this sequence converges to some value, and that is E. So we define this E to be the limit of this sequence. And if you calculate this, then that's something like 2.718 and so on. Okay, so that's all for this video. See you later.